Hi there again. This is our second test and last test of the day, anyway, that you're gonna learn about today. It's called the limit comparison test. It's another test that we can use to show whether or not a series converges. So, in all this description of the test here, AN is the series that we're wondering about. Okay, so in order to use the limit comparison test, we have to have a series that has all positive terms. So that means A of n is greater than 0. Just means all the terms have to be positive. And like the name suggests, this is a comparison test. So there's another series, that's Bn, that we're going to compare it to. And I'll show you in a minute how to figure out what to compare it to, what that Bn series will be. But for now, just know that it's a series that we're going to compare it to. We have to figure out what it is, but it's not too hard. And initially, they actually can be negative at the beginning. Some of the terms can, as long as at some point they turn positive and they stay positive. We're okay. Okay, so we find the limit as n goes to infinity of the series that we're interested in over the series that we're comparing it to. And if we get a positive number, not 0, not infinity, but a positive number, then both of those series either converge or they both diverge. So that's one scenario. If we get 0 for that limit and the series we're comparing it to converges, that means the series we're wondering about also converges. Remember, AN is the one that we start with. And if we get infinity for that limit and the series we're comparing it to diverges, then AN diverges. Now, if you get 0 and BN diverges, this test won't work. If you get infinity and BN converges, this test will not work. So there's only 3 scenarios here where this thing can work. But it's actually a pretty powerful test. So well, let's see. So here's a couple of series, a couple of examples we're going to do. So this is our AN. This is our AN series in the description up here.
Sometimes I want to kill kids.
Okay, so this is our AN series. This is the one we're wondering about. We've got to figure out what to compare this to. We've got to figure out what that BN series is. And we look at what the series looks like as n gets big. Okay. As n gets big, this series, let's see, 2n plus 1 over n plus 1 squared. As n gets big, this plus 1 right here becomes more and more insignificant. Oops, I don't want equals. They are not equal, but this, so the top of that, the top of the terms start to look a lot more like just 2n. Because again, the plus 1 becomes insignificant as n gets big. On the bottom, if we were to multiply this out, we'd have an n squared term, we'd have an n term, we'd have a constant term. And the n squared is the one that would dominate on the bottom. So the bottom of this would look a lot more like n squared. Now you can actually simplify this, which we will want to do. Those n's will cancel. And so what our series starts to look like, as n gets big, it starts to look a lot like 2 over n. Now this is Bn in the description above. You look at what your series looks like as n gets really, really big. And it starts to look like 2 over n. Now, what do we know about 2 over n? Well, that's a p-series, right? If you can take the 2 outside, 1 over n, that diverges. By the p-series test. So now for the limit comparison, there is a limit that we have to calculate. And it's the limit of our original one, 2n plus 1 over n plus 1 squared. And we've got to divide that, right? In our description, we had an over bn, right? An over bn. We've got to divide that by the one we're comparing it to. And this was our bn. It's what our series looks like as n gets really, really big. So we're going to divide by 2 over n. I'm going to skip that step and write times n over 2, multiplying by the reciprocal. You don't need an absolute value on this one. They're all positive terms anyway, so it doesn't matter. And then we find this limit. Well, all we got here are powers of n. So if we were to multiply the n by the 2n plus 1, the highest power of n would be n squared. And it would be 2n squared. The highest power of n on the bottom would also be 2n squared if we multiplied everything out. So since they're both n squareds, we look at the coefficients. The coefficients are 2 over 2. And so our limit would be 2 over 2 is 1. So let's see what scenario up here we got. So we got 1 for that limit. That's not 0. It's not infinity. That is a constant. So in this scenario up here where we get 1, where we get a constant number, both of these, either both of them converge or they both diverge. Now, we got 1, and the series we were comparing it to diverges. That means our series also diverges. Let's take a look at this other one over here. So again, this is our an. We want to know, as n gets big, what does our series start to look like? Well, as n gets big, this minus 1 on the bottom, like subtracting 1 from 2 to the n, like 2 to the 1,000th minus 1, it might as well just be 2 to the 1,000th. Right? The minus 1 becomes insignificant. So this starts to look like 1 over 2 to the n. Now, and that's our bn. That's the one we're going to compare this one to. Now, what do we know about 1 over 2 to the n? Well, that's geometric. Right? The first term would be 1 over 2. The next one would be 1 over 4. Next one is 1 over 8, 1 over 16, plus 1 over 32, plus 1 over 64, and so on. You're just multiplying by a half. That's a geometric series. And 1/2 is less than 1. So this one converges. And we'll just say it's the geometric series test. Okay, don't have to spell that out for now. So let's find our limit. Limit as n goes to infinity of the one we start with, 1 over 2 to the n minus 1, divided by the one that we're comparing it to. The one we're comparing it to is 1 over 2 to the n. So I'm going to multiply by the reciprocal. Okay, so that's 2 to the n over 2 to the n minus 1. Well, as n gets really, really big, 2 to the n and 2 to the n minus 1, they start to look pretty much the same. I mean, the bottom is just 1 less than the top. They're going to be really, really close together. When you have a fraction that's essentially the same on the top as it is on the bottom, that fraction is going to equal 1. Now, we just happen to do 2 examples here where the limits were both 1. You don't always get 1 here. The important thing to note about this limit is that it's not 0 and it's not infinity. Okay? So let's go up to our scenario here. Our limit wasn't 0. If it was 0, we could use this. If it was infinity, we could use this, but it's not. It was 1 again. And this thing tells us that the series either both converge or they both diverge. So let's look at what we got here. We got a 1, which put us in that scenario we just looked at. 1 over 2n converges. It was a geometric series, so it converged. That means the one that we're looking at, or the one that we're wondering about, also converges. And that is the limit comparison test. Your assignment for today is on page 523. Oops, 523, excuse me. Number 7 through 17 odd. Page 523, 7 through 17 odd. Good luck. Bring your questions on Monday if you've got them. Have a great weekend.